Thank you very much. Thank you for welcoming me to this talk here in Vienna. Okay, I'm going to give you a talk on this TULIPP European project about computer vision, but maybe first, oh yeah, exactly. I'd like just to take a minute to introduce my company. HIPPEROS is a spin-off of the ULB, Université Libre de Bruxelles, concentrating on middleware operating systems. And in reality, it's not a generic operating system company. It's a company focused on what we call intelligent autonomy. Basically, it's a company focusing on high-performance middleware operating systems for applications such as computer vision, which, as you know, has a lot of very challenging applications. And we believe that very challenging applications basically require high-level, high-performance, highly reliable also middleware and operating systems. Now, I don't think I need to explain for this audience that you have image processing, computer vision everywhere, from robotics, industrial control, space, defense, drones, all over the place. And we are facing a challenge over there. Basically, the challenge is we have an increased number of sensors, more and more sensors, the amount of data, the bandwidth really becoming limiting factors. But we also have other challenges, like the issue that we demand high performance. We demand very high frame rates, and all that into embedded devices which have typical constraints like low power, like limited, like latencies. I mean, basically what we're trying to do into this business is to fit the computing capabilities of a supercomputer into something like an embedded board like that. Okay, in order to answer this challenge, basically it means to combine image-sensitive processing systems with all these time, security, etc. challenges, with all the embedded constraints like the low power, the limit of the size of the system, weight, etc., but also in situations where you are market sensitive, time to market, cost sensitive of the device, but also cost and time to develop the application. So basically, how do you go from an algorithm that you develop on your own or on research lab into an embedded devices, into a car or a plane or an industrial equipment? In order to solve this challenge, 1.5 years ago, approximately, we started doing a H2020 research project, where you see the partners over there, the main contractor being Thales Research in France, with the focus on solving the high-performance, real-time image processing challenge on low-power platforms. What we want to do for that, as I said, is hard real-time image processing, high reliability, even to make certifiable systems. We need high performance because most of the machine vision algorithms are very demanding in terms of computer power. And basically what we want to do is not to delegate the computing to the cloud with some external server. We want to do this on the device. We want even in some cases to do it on the edge device, intelligent cameras. Basically part of the requirements is that we need to support hardware acceleration, low power, and last but not least, in many, many industrial challenges, we have security. You don't want anyone to tamper with your device, so we must take care that the device is secure, that the system is secure, and that even when you do field upgrades or you roll out new applications, your device is not compromised and somebody cannot, let's say, tamper with the automatic driving system of your car. Together with those technical requirements, we have also industrial, economic requirements, like reduction of the time to market, reduction of development cost and effort, the risk. Also, we wanted to do evangelism on the low power embedded high performance. We wanted to communicate into this community. And therefore, in this project, we went into basically providing two outputs. One is giving guidelines for efficient development of the complete computer vision. It's not just the hardware, it's not just the algorithm, it's all together. And also the other thing that we wanted to do is to provide some standardization in terms of a generic platform. And when I mean standardization, it doesn't definitely mean one single reference platform, it means providing a reference platform within a set of genericity so that people can still plug in their own hardware or their own operating system or their own algorithm within this generic platform. Okay, the typical image application, computer vision application that we are looking at are things like that. Image size from just a few hundred pixels to really megapixel. 16-bit per pixel could be more, but that's typical application. And very important in our case was the real-time aspect. We are talking about systems which start with something like 4 to 5 frames per second up to hundreds of frames per second, with the hard real-time constraints that you find in many industrial applications of 0 frames mix. You are not allowed to miss frames either for certification or for reliability. And you have data sizes, data bandwidths from roughly 30 to 60 megapixels per second. Part of the real time is not just not missing frames, it's also the low latency. So we typically have very, very low latencies. And the question here is not so much the average latency for processing a frame, but the maximum. The worst case latency for processing a frame is in very many industrial applications, the real constraints. Typical kind of processing that we're talking here in terms of the processing pipeline is a multi-stage, where typically in the first iteration we have some basic image correction, image enhancement, image filtering to get a clean over-processed image. And then we have the second stage of processing, which is the real complex image processing, which is application-oriented, where you could do some machine learning algorithms or stuff like that. Okay, the overall project, I'm not going to go into the details over there, but this is basically the traditional structures of this large European projects. So basically you start with requirements, formalization of the requirements of different use cases. I'm going to go into that. And then developing the technology packages, and then basically showing the results and showing how we have built our required results based on the technology requirements and applying them to the use cases. So it's part of the TULIPP. What we're doing is, as I said, set up an ecosystem, work closely with the standardization organizations in order to promote this platform, and of course propose new standards, propose benchmarks, propose good practices related to this. Okay, the main concept of the TULIPP platform is the idea of a plug-in, plug-and-play or generic reference platform. The reference platform that you find over there consists on the one side of the hardware platform, processors and hardware accelerators, so such GPUs, FPGAs, or other kinds of accelerators. Then you have the operating system and the middleware layer, so basically everything that is concerned with, I would say, giving access to the hardware to the high-level programming paradigm. So the middleware, the libraries, operating systems, scheduling, synchronization. And then you have all the application components, all the application algorithm. And last but not least, I shouldn't forget it, is the toolchain aspect. I mean, when you're designing a system like that, it's very also difficult to do all the design space exploration, all the choice of tools, also translating the algorithm for a high-level language to something, for instance, like VHDL for the FPGA. All of that should be facilitated by using so-called toolchain, by using so-called tools that allow you to make this kind of a system without mastering all the details down to the hardware. So basically, it's given an abstraction so that someone can go from the algorithm to the fully deployed board in the easiest possible way. All right. Just a few words about the reference platform. As I said in the beginning, it's not the idea of just making this platform, or we had to make a choice for a reference. The reference platform that we're using is a Sundance board that contains a Zinc 7000 series chip containing several ARM cores, as well an FPGA from Xilinx. This is what we are using now. We are going to go into just something like 3 months. I mean, the work is ongoing to the new Zinc UltraScale. The advantage of using this is that it supports, in particular, low power features that we were very much interested in, so that switch-off mechanisms for parts that we are not using, DVFS, as well as dynamic partial reconfiguration of the FPGA, which will allow to load on the accelerator just the filters that you need when you need them. So it gives you a way to really choose which algorithms and which accelerations you are, depending on what the application requires and what even the mode of utilization of the application is required. So this is just to give you an overview of the hardware platform. I'm not going into the details, as you have all of this on your handouts. The layer on top of that is the operating system. This is the HIPPEROS RTOS. The main characteristics of the HIPPEROS RTOS is that a low footprint RTOS that was specifically designed for this kind of platforms. It's parallel, multi-core, and it supports not only these low power features like DVFS, etc., but it also supports the hardware acceleration in a smooth way. So it gives you the possibility to combine the hardware accelerating processing with the software pure CPU task in a very smooth way, in such a way that you don't miss frames, that you don't miss deadlines, and that you keep maintaining this very time-bound, very deterministic latencies for the processing. So it's really the kind of operating system that is much more efficient on this kind of platform than if you use just a standard Linux platform or even an RTOS which is not dedicated for this. It's really an advantage in terms of reliability and in terms of performance. These are some characteristics of the HIPPEROS RTOS. It's an RTOS that was developed by the HIPPEROS company itself, coming from many years of research at the ULB in Brussels, with some support from European Space Agency and other sources of funding because of the criticality of the kind of applications that we are doing with this. The Toolchain aspect, the Toolchain is being developed by NTNU in Norway, as well as a group at the Ruhr Universität in Bochum. It's called STEM, and the idea of this Toolchain, again, is to give a high-level development environment for people wanting to develop image processing applications, so that everything is as smooth and as easy as possible in order to lower the learning curve required to go from algorithm to fully deployed computer vision application. Now about the use cases. These use cases are the use cases that we are making within the project. So of course, the platform is not limited to these 3 use cases, but we believe they are representative. Use case for medical imaging, automotive imaging, and robotic imaging, with the characteristics, as I said, of high performance, power consumption, and all the embedded constraints and real-time constraints. First of all, the medical imaging use case. The idea of the medical imaging use case, which is a use case from Thales France, is to do image processing in surgery. If you want to do image processing during surgery, basically you are irradiating your patients, and you will very well understand that if you use a very high dose of radiation for an operation that takes, let's say, 2 or 3 hours, your patient will not appreciate that. Okay? So in order to avoid that problem, the basic idea here was to reduce the amount of radiation, so to reduce the amount of photons in a certain way, okay, which means that your image is very low quality. Your image is blurred, your image is not very well defined, and therefore what we need here is to take a very blurry, a very low quality image, and to do the image enhancement in real time so that the surgeon can have us in monitor, or the robotic surgery system can have on its monitor an image that really gives the correct information. So here you have an example of a blurry image on the left side, and on the right side you have the same image after the enhancement algorithms. With, last but not least, with a radiation that was reduced by 75%. Okay, so this is the setup that is changing for the image processing case. Second use case, this is a use case from a Swedish company. Synective is an ADAS use case, so it's basically the board that is being put into a car or into a lorry or into an industrial vehicle that detects the obstacles, detects and identifies vehicles or pedestrians or people on the bike in real time and is able to inform the driver. And of course, all of this is something that we want to put into a very low-cost, low-power board, and not just like in some of the current prototypes where you need to have 40 or 50 kilogram computing power in your car that uses something like 200, 300, or 400 watts. Basically, the board that we have here consumes something like 10 to 12 watts, which is a very, very different story, of course. Okay, so here you have the kind of integration that is done, pedestrian detection, and then using the safety advanced application also on the same board. So we need to have both the image processing and the application on the same board. Third use case, which is a use case where the driver now is the Fraunhofer Gesellschaft IOSB. It's autonomous drone flying with image detection, 3D depth maps. And the idea here is to fly these drones into typically rescue areas in order to fly autonomously and detect something like victims that need to be rescued. This is something what we want to do with fully automated flight, and therefore we need to embark this kind of computing power also on the drone. That means, again, low power and also low weight board for the image processing application. Okay, this is basically what the project is about. We are now roughly 1.5 years, so we are the half of the project. What have we achieved so far? First of all, we have achieved to include into our setup the possibility to do VHDL synthesis from C-source automatically using some external tools. Of course, we don't mind to develop everything inside. So basically, we can start with a basic algorithm or a complex algorithm written in C and determine which parts should be better performed by the FPGA, and we are able to synthesize and to deploy with generated FPGA code. The STEM toolchain, the HIPPEROS, have been integrated with the Xilinx tools for the high-level synthesis, and which have achieved a transparency from the algorithm developers to the middleware and to the hardware people. So we are really able now, for the very, very early versions of the prototypes, to go through the board, from the source code to the board, basically as an automated way. To give you an idea of the performance, if we do the kind of demos that we are doing for the moment, and we have a little demo set up over there, if we do that with this board, without using the hardware acceleration, we achieve something like 4 to 6 frames per second. If we do this with the hardware acceleration and with all this synchronization of the operating system for the data flows, we achieve up to 90 frames per second. Again, as I said, without losing any single frame, with a very limited latency. The role of the operating system in this setup is, of course, the synchronization of the hardware, software task, and the data flows, the handling of the low power. So you could imagine a setup where the images are being captured, you're running on a lower rate, you don't need necessarily to power the full FPGA, or you don't necessarily need to power all the cores, and then suddenly you detect some feature that requires an accelerated processing, and then you switch on all the cores, which is on other parts of the FPGA, and then you parallelize some computing, like some machine learning that really needs all the power. When that is finished, you go down the power reduction. And this is something that we have done some experimentation that shows that we can spare 20, 25, up to 30% of the power of the platform. The last achievement here, which is something we're quite happy with this, we have been able to achieve FPGA dynamic partial reconfiguration during the processing of the tool. This is, again, is something we have achieved for the moment at the technological level. What we are going to do for the rest of the project is basically find the ideal ways to use that FPGA dynamic partial reconfiguration, and you can think in terms of choosing different filters depending on the kind of application, or choosing different filters of the different image enhancements depending on the task at hand, and doing all that in a in a board with quite limited computing capabilities for all of this. So we need to be very, very efficient in the way we use our board. Last but not least, as part of our mission from the EU within this H2020, part of our mission was to build a community of users for this kind of low-power real-time image processing platform. Therefore, we have set up something we call an advisory board, but which is in fact more like a users group. And anyone that is interested in this technology, anyone that wants to try out these technologies, get the guidelines, get some evaluation boards, well, please join us. We'll be more than welcome, and it's obviously free. It's not only free, but you also get some of the early results and some of the development boards so that you can try out for yourself. Thank you very much. I do have, yeah, well, just to give you an idea who is in there for the moment. These are some of the current, it's not even up to date, it's really growing. These are some of the current advisory members. You find people from academia, but also from industry, of course. This is in terms of dissemination, where we are really explaining the results and informing the community about our results. And if you are interested more into the scientific part behind all of this, here are some references for you with some papers, with some of the scientific results, etc., etc. Well, thank you very much.